Let us look at the TugOWar example that we did in class. So what did we do? We had two students and these two students were holding a rope, so they're standing on the floor, and we had a third student that was standing in the middle, or actually this was me, and I was pushing down the rope. So the rope was pushed down. The students are pulling both in this direction, and I was pushing down, and let's assume I was pushing down with force of 25 pounds. Now what we wanted to figure out is, in order to hold this, what is the force that the students need to apply to pull the rope straight again? So the first thing we want to do is we want to draw down a so-called free body diagram. So what we do is we define a coordinate system. I give it names, x and y axis, and I also indicate the directions. What is the positive direction? What is the negative direction? The point of the rope that I'm pushing just becomes a dot here at the center, and now I have to draw in all the forces that are acting on that point. So I have one student pulling in this direction. Let's say this is the force F1. And I have another student pulling in the opposite direction, and this is the force F2. And I'm pushing downwards at a force of F3, and I know this is 25 pounds. Now let's assume that everything is symmetric and that this angle is the same as this angle. So this is the angle theta. Let's assume the angle theta is 5 degrees. These vectors here have now components. This here is the y component of F1, and this here is the x component of F1. This here is the x component of F2, and this here is the y component of F2. So I can find the components of each of these two vectors F1 and F2. So F1x divided by the hypotenuse F1, that equals, it's the, here this is the adjacent divided by the hypotenuse, that is the cosine of theta. From that it follows that the x component of F1 is the magnitude of F1 times the cosine of theta. F1y is then F1 times the sine of theta. That's the opposite. Also what we find is of course then that F2x, that is the magnitude of F2 times the cosine theta. The x component is adjacent to the angle theta. Now we also have to recognize that this points into the negative direction, so it's a minus sign here. F2y, that is the magnitude of F2 times the sine of theta. That is positive again. Yeah, so these here are positive, and F2x is negative. Also what we have is F3 is strictly in the y direction, so F3 is just minus F3, and F3x is not pointing in the x direction at all. This is 0. So we have all these components. Now we can apply Newton's law. We do know that the sum over all forces which are acting is the mass times the acceleration. In static equilibrium, the acceleration is 0. So nothing is moving if I'm holding it in place there. I can apply this now for the x and the y components individually. The sum over all forces in the x directions, all x components, is mass times ax. And because a is 0, of course ax is also 0. What are all the x components? It is f1x plus f2x plus f3x, and that has to be 0. I know what all these components are, so from that it follows f1 times the cosine of theta plus f2 times the cosine of theta. F3 is 0, so that is 0. And I made a mistake, because this component here was negative. So this has to be a minus sign here. So, from that it follows that f1 times cosine theta equals f2 times cosine theta. I can divide left and right by the cosine of theta, and from that it follows that the magnitude of f1 is the magnitude of f2. Let's just call this just f. So they're both pulling at the same force, provided the angles are the same. So each pulls up at the same angle. So we know these two forces are equal in magnitude. Now I can look at the y direction. The sum over all forces in the y direction equals may. Because nothing is moving, ay is also 0 in this case. So I have f1x, f1y plus f2y plus f3y, that is 0. I know what these components are. They are f1 times the sine of theta plus f2 times the sine of theta minus just the magnitude of 3. Force that points down. f1 and f2 are the same, we can just write f for it, so I get f times the sine of theta plus f times the sine of theta. Bring the f3 on the other side plus f3. So I get 2f times the sine of theta equals f3. From that it follows now that the force that the two students have to pull with is f3 divided by 2 times the sine of theta. So it is 25 pounds divided by 2 times the sine of 5 degrees, and what this turns out to be is 144 pounds. What we see is that the force at which they have to pull is my force divided by the sine of the angle. So if this is a small angle, the sine is small too, and they need to to pull at a much, much larger force. For a very shallow angle, this force can reach several hundred pounds, or maybe even 1,000 pounds. Let's look at an example. What would be for theta equals 90 degrees, so this means the students pull straight up, so they're pulling both up, and I just push down. From that it would follow that the force that they need to apply, the sine of 90 degrees is 1, is just my force divided by 2. In that case, they only need to expend half of my force. So if they pull straight in the opposite to my direction, they will win. If they only pull at shallow angles, they cannot win this.